All right, probably we'll get started. I hope I'm audible to everyone. Um, and my recording is also ongoing. Okay. Probably maybe I'm currently in a bad network situation, so probably I will switch off my video and whenever it is required, I will switch it on. Okay, so that we will have a smooth connection. All right. This week we studied about internal force convection. Professor Suman was talking about internal force convection, especially for uh, flow between a parallel plate and also flow inside a circular pipe, right? Uh, so we'll quickly go through what has been discussed in the uh, you know classes, and after that, I have two problems, more like a derivation type problems, and we will solve that. And if you have any questions, you can ask me later. Okay. Before the class begins, do you want to ask any questions? If so, please do so. If not, I will continue with the today's topic. All right. Thank you, Avinash and Krishna Kumar, for joining. So I hope there is no uh, questions from your side. Maybe I will go forward with the today's topic. It's about internal force convection. So initially we started with this, uh, you know, flow between a parallel plate, and we realized that there's going to be hydrodynamic flow development, and also thermally also there will be a flow development, because at the entrance you do not have any profile. It's a linear or uniform profile, and when it sees the pipe edge, it has to uh, have a no slip boundary condition over there, and because of that there will be a profile development. Then basically there will be a boundary layer development, and the boundary layer will be developing on both sides. Here it's a 2D parallel plate, so at the top and bottom, the plates, you will have boundary layer development, and at one point they are going to merge, right? And after that you will have a hydrodynamically fully developed flow. So that is what we realized. And similarly the same thing is going to happen for thermal, uh, for the temperature profile too, right? And this is how parameters vary. We all know why this varies like this. It's a fluid dynamics. In fluid dynamics itself we studied this, and we introduced a new concept called bulk mean temperature, which is basically, if you are defining a heat transfer coefficient H for this kinds of problem, you are going to use bulk mean temperature. Okay. And the bulk mean temperature definition is something like this. It's nothing but a cross-sectionally averaged temperature. So along this cross-section, the temperature profile is going to vary. Initially, it will be T wall, and probably based on whether the temperature of the fluid is higher or lower. In this case, it's higher. Then you will have something like this. I should not draw arrow mark. So your temperature profile would be something like this, right? Since it is continuously varying across the cross section, we can have an averaged cross sectional temperature, and that is what this bulk mean temperature is. And if you, let's say rho and CPs are constant, then your definition simplifies further, which is what we are going to deal with for this course at least. And uh, and then we found out that, let's say if you want to find the Nusselt number, then for a thermally fully developed flow, after the boundary layer is merged, then the Nusselt number remains constant, because H by K is constant. So based on this simple heat flux analysis, we can clearly say that H delta T by K is goes as 1, which means it's going to be remain constant, while in this case the delta T is going to be the thermal boundary layer thickness, is going to be the plate separation distance, which is in this case H, right? Basically 2H, but here the thermal boundary layer thickness is going to be half of it, H by 2H by 2, which is H. So this, based on this, we can define this is a Nusselt number correlation, or based on this, we can define this as a Nusselt number, and if this is the Nusselt number remains constant for thermally fully developed flow. Okay. Now, and then we can, non-dimensionalize this, and we did this, and then we found out that theta is not a function of x, which means it is not a function of axial direction for a thermally fully developed flow. And we are going to deal with thermally fully developed flow for the entire analysis. We are not going to worry about that initial part where the flow is developing. Okay. And and we had two cases, constant T wall and also constant heat flux cases. And based on this definition of T mean, actually we can define dou T by dou X to be, or we can derive it and we can show for thermally fully developed flow, dou T by dou X is theta times dTm by dx. Here Tm is just a function of x, it can only vary along the x because we have averaged along the y. So T mean can only be a function of x. So this is how you can replace the partial derivative of temperature with respect to x as simple derivative of T mean or T bulk, right? Similarly, for constant heat flux, if you perform the similar analysis, you will end up having this to be constant. Okay. So basically, the actual temperature gradient is nothing but your actual uh, mean temperature gradient. Okay. All right. And then we did energy balance to show what is this dTm by dx, and it turns out to be heat flux times perimeter by m dot into Cp. So it's a simple heat balance that we can do for this kind of control volume. And important thing is we have neglected the axial conduction. That is, if because of this assumptions, we have a simplified dTm by dx relation. And if it is a constant wall heat flux, as we said, this dTm by dx is constant. And you can also see from here, this m dot is constant, Cp is constant, perimeter is constant. And since this is a constant heat flux problem, this whole thing is a constant, and hence this is also constant. Okay. So it even if this is not a thermally fully developed flow, if you simply say that heat flux is constant, then dTm by dx is constant. Okay. And this is how a typical temperature profile would look like, just for your understanding. And similarly, if you do a constant wall temperature, how would the profile look like? Then you will have something like q dot is nothing but something like LMTD, logarithmic mean temperature difference, right? And so this part is LMTD. We call it delta T LM here, and we can define this as delta TL by delta T naught divided by logarithm of delta TL by delta T naught. All right. Uh, this is about both the conditions: constant heat wall heat flux, and the constant wall temperature. And we are going to go forward and study how will you find the convective heat transfer coefficient, and also eventually the Nusselt number for problems of forced convection, right, inside a parallel plate or pipe. And we are going to ignore this initial part, especially. So we call this as a grades problem, where in this problem they will study about once the fluid hydrodynamic boundary layer is developed, but still thermal boundary layer is developing. So the region where they study this part is grades problem. But we are not going to study any of this. We are going to study only hydrodynamic and thermally fully developed flow. And uh, initially we started with parallel plate, and in the parallel plate, the first case is constant heat flux. Constant heat flux is fairly easy to solve than constant wall temperature. And this is our energy equation. In the energy equation, because of constant heat flux, we can simplify certain things. This can be replaced as dTm by dx. And we know fully developed flow based on continuity equation, we have V to be 0. And for constant heat flux, we know that dou T by dou X is equal to constant. So because of that, then the derivative of this is going to be 0. So this can also be simplified, and you will end up having a simplified energy conservation equation. And if you solve this, you will be able to get the temperature profile. And once you know the temperature profile, you can find the Nusselt number, right? And since we always deal with the non-dimensional parameters, we did the non-dimensionalization in terms of theta and y bar, and then we know this dTm by dx for the heat, for the constant wall heat flux. We can simplify it, and then we substitute it, and then you will end up having a simpler equation, something like this. Now this is just a ODE, right? Which you can analytically solve it. That is what we did it here. Here we have u by u bar, so we need to know the velocity profile in order to solve this equation. So that is something we already know from our fluid dynamics class. For Poiseuille's flow, this is how our velocity profile varies, and for a plug flow, it's nothing but plug flow means there's no development of boundary layer, or it is very small. You can simply say u by u bar is 1. Okay. We will solve this in today's class. What happens if you do a plug flow? Here we did for Poiseuille's flow. So to increase confidence on solving these kinds of problems, we will solve this plug flow in today's class. Okay. And then we applied certain boundary conditions because this is an ODE, and we end up having a relation for the temperature profile. Now, but this temperature profile is in function of Nusselt number and y bar, but we need Nusselt number. So we use the definition of Tm, and then we simplified and came up with that condition. And once you solve this condition, you will end up getting Nusselt number. That is how we do it, right? And then we define something called hydraulic diameter, and then we did it turns out to be 140 by 17. Similarly, we can do for constant wall temperature, and in the constant wall temperature, the approximation of dou T by dou x is going to be theta times dTm by dx, and velocity, v component of velocity is 0, and this component is going to be 0 because we are going to neglect the axial convection. That's why this is also an approximation, and then you can do non-dimensionalization, and you will end up having this relation. The equation, this equation is different from the previous equation because of this theta. Okay, so only this theta, the difference in theta is going to affect the uh, way of solving this, and because of this theta, we are going to end up having difficulties in solving analytically. So we have to solve it using numerical methods and something called shooting method. Basically, we have this equation. Shooting method is nothing but we have this equation ODE, and then we have a couple of boundary condition, and actually the third boundary condition is also there. So what we have to do, basically we have two boundary condition and one initial condition. So we have to specify an initial condition and boundary condition, and then march in space and reach the other boundary and check whether the other boundary is same as the condition that we have, and if it is same, we have reached a convergence. If not, we change our initial guess, and then we will repeat it. So that is what we do here, and after this iteration you will end up having 7.54. I will leave it up to you. If you can code this in MATLAB and check for yourself, it would be great. If you face any difficulties in programming this, please let me know. I will be able to help you. Okay, so if you solve this, so basically we know f is nothing but u by u bar, and uh, we also know uh, this is the equation, so you can simply use ODE 45 or something like that, and you'll be able to solve this. If you want in detail an algorithm, I will be able to give it to you. Okay, so please let me know about it. And going forward, and then this is parallel plate till now we did, and now we will go into circular pipe. In circular pipe, the energy equation is little bit different. The energy equation is based on cylindrical coordinates. We have r, z, and theta, and uh, we are going to assume it's an axisymmetric problem, so there's no variation in theta. There's only variation in r and z direction. Okay, all right. And we are going to assume it's a fully developed flow. So the initial case is constant wall heat flux case, and in that this is going to be remaining same. For fully developed flow, here VR is 0, and this part is also 0. Dou t by dou z is same as dou t by dou x along the axial direction. It is constant. Dou t by dou x is constant. So the second derivative is 0. That is what we did here, and then we can simplify it. And once you simplify it, you will end up having finally this as your simplify it plus non-dimensionalization. You will end up having this equation. Okay. Now again we need to know the Vz by V bar thing, which is coming from fluid dynamics. So we need to know when there is a flow between a circular pipe, what is my velocity profile? And once only if we know velocity profile, we'll be able to solve this equation. Okay. Now we apply this for Hagen-Poiseuille's flow. Because we already know the velocity profile here, and you can substitute them, and then you can simplify them, and then you will be end up having when you simplify it again, you will end up having theta to be as a function of Nusselt number and R bar, right? And but we need to know Nusselt number in terms of diameter, and hence what we have is we have to use the definition of Tm like we did in the previous time, and you will have you have to perform this integration, and you will end up having 48 by 11. Okay. Similarly, we can do constant wall temperature. Again, that is going to lead you to nonlinear ODE, which you can't solve analytically. Uh, Hence, you need to use numerical methods, basically shooting method, and you will be end up having the Nusselt number, which will be 3.66. Okay. And then we also saw there is something called calibrated correlation for turbulent flow. This is based on experiments, and this is how the Nusselt number correlation would look like. As we have studied even in the external flow, the Nusselt number here also depends on Reynolds number and Prandtl number, but the exponents are a little bit different. Here the Reynolds number to the power zero point 0.8 and Prandtl number power n, where n is 0.4 for heating and 0.3 for cooling. Okay. Yeah, but these doesn't come by solving energy equation. It comes from experimental observation. People have performed experiments. They measured the temperature profiles, and they found the Nusselt number for various Reynolds number and Prandtl number, and then they fitted this kind of correlation for it. And this is the most celebrated correlation, Dietz-Boulter correlation. That's why we need to show a little bit about it. So we have included in our syllabus. Okay. I hope this is clear. It's a fairly, proper steps you need to follow. Basically, you need to solve energy equation, but in addition, you need to take into account. I mean, you're just modifying your energy equation in terms of bulk mean temperature, and when you do that, you will simplify your equation. Once you simplify your equation and the boundary with the set of boundary conditions, you will be able to solve it. That's the whole idea. I hope this is clear. I just gave you a quick recap of what has been done this week. I think the last part you may not know because it is in the week 10. But for the sake of completeness, I already showed you. I think probably, I don't know which one is it. Anyway, it's just the same thing again. Don't worry about it. Any questions till now? All right. Hopefully, there is no questions. If there are any questions, please let me know. I hope I am audible and you are able to follow me. Okay. All right. Then we will quickly go to today's questions. I have two questions, one and two. As I said, one is going to be the plug flow. The other is going to be is to just to find Nusselt number based on given velocity and temperature profiles. And I saw your assignment problems. The assignment problems are more like mostly descriptive, and if you follow the lectures properly, you should be able to handle those questions. I no need to give special importance for that, and I'm sure that if you understand the methodology, you should be able to answer those questions. In case if you have any doubts, please let me know. Um, I'll be happy to explain it to you again. Okay. All right. Then we will go forward and solve this question. So the first question we have here is for the flow of a liquid metal through a circular tube, the velocity and temperature profile at a particular actual location may be approximated as being uniform and parabolic respectively. Okay, so the velocity profile is uniform and temperature profile is parabolic. That's what they are telling. So the profile is also they have given, where C1 and C2 are constants. What is the value of Nusselt number at this location? Okay, so at a certain location, we can approximate the velocity profile and parabolic velocity profile and temperature profile as two different thing. So it's a circular tube. So probably I will draw an schematic here. Um, so this is how your pipe looks like. So here, and then you will have something like this. Now, just give me a minute. All right. So, um, here, this is our, so probably we can say this as R naught, and this is our radial direction. This is our actual direction Z. Now, uh, at any location, at some location, let's say this is the location, they have the velocity profile and they have the temperature profile, T of R. So let me write that down here. U of R is equal to C1 and T of R is equal to Ts plus C2 times 1 minus R by R naught square. So the velocity profile is uniform and while the temperature profile is parabolic. Okay. Now we have to find the Nusselt number based on diameter NUD. Okay. That is how we need to find out. That's what we need to find out. Now, if you think about it, how would you define Nusselt number? It is going to be HD by K. Now, K is a property. D is something we know, which is nothing but H into 2 times R naught by K. Now, only thing we need to find out is R naught is also the, based on the design of pipe. We can't do anything about it. Only thing is we need to know is H. So if you know H, so what is H? If you know H, you can find the Nusselt number. If you want to know H, how would you find it? The only place where we deal with H is heat flux, right? So let's say if we express heat flux, wall heat flux is going to be H times T wall minus T m. Okay. Here I think wall is nothing but this is surface, right? So we can express it as yes, Ts minus Tm. Okay, this is how heat flux is defined. So we can write H in terms of this. H is nothing but heat flux divided by Ts minus Tm. Tm is a bulk mean temperature. Okay. Um, what did we? How did we define this? So Tm is bulk mean temperature. Okay. Now we need to know bulk mean temperature. We need to know Q wall, heat flux. Once we know these two, probably we can find H, and if we know H, we can find the Nusselt number. Okay, that is the way that we are going to solve it. So first, let's try to find Tm. What is Tm? So from the definition, we know that Tm is going to be, what did we found here? So for constant rho and constant Cp, it's nothing but integral of sorry, integral of u t dA divided by integral of u dA. Okay. Now this is a circular pipe, so dA you can replace with 2 pi r dr, right? That is your elemental area. So you can write this as integral of u t 2 pi r dr divided by integral of u 2 pi r dr. So we know that u at this location is going to be simply C1. Okay, so we can just substitute that too. What happens if you do that? Equal to C1 is a constant, so you can take it out of integral C1, and these integrals are going to be 0 to R naught. Okay, so remember this is an you know in cylindrical coordinates you have 0 to r naught only. It's not like minus r naught to plus r naught. Okay, because your what do you call, the coordinate frame is fixed at the center, you can only go from 0 to r naught, and along the theta direction we are integrating. That's why it's 2 pi r. 2 pi is the theta direction. um, 2 pi is 360 degree times r dr. Okay, so your integration will be from 0 to r naught. So this becomes integral of 0 to r naught. 2 pi is also constant, we can take it out. 2 pi into t times r dr whole divided by c1 2 pi integral of 0 to r naught r dr. Okay, so this is nothing but we can remove this c1 2 pi, and we can write this as, so the denominator integral of 0 to r naught r dr is nothing but r square by 2, right? So we can write this as r naught square by 2, so we can write this as 2 by r naught square integral of 0 to r naught t times r dr. Now we know the temperature profile too, so let's substitute that. T is Ts plus C2 times 1 minus R by R naught square. So let's substitute that. Equal to 2 by R naught square integral of 0 to R naught R into Ts plus C2 into 1 minus R by R naught square into dr. Okay, so now it's just a simple integration. R naught square. So the first term would simply become Ts. Ts is constant, so Ts you can take it out, and R into dr. R dr is nothing but R square by 2, and if you substitute the um, limits, it becomes R naught square by 2. Other side is 0. So you can write simply as R naught square by 2 plus, similarly C2 times R will be there. Again C2 R dr, you can write as C2 R square by 2, and if you substitute the limits, it becomes C2 R naught square by 2, and finally you have C2 by r naught square into integral of r into r cube dr, right? 0 to r naught. So this becomes r naught power 4 by 4 basically. So let's do that too. It will be divided by r naught square ts r naught square by 2 plus c2 r naught square by 2 minus c2 by r naught square into r naught power 4 by 4. So this you can cancel this, then it becomes c2 r naught square by 4, and you can couple these two, it becomes c2 r naught square by 4. So let me write this down, and then you can take the 2 by r naught square inside, this becomes ts plus um, c2, or maybe I will take one step ahead, 2 by r naught square into ts r naught square by 2 plus c2 r naught square by 4. Now you take the 2 by r naught square inside, it becomes ts plus c2 by 2. Okay. This is your tm, and actually we can just simply write ts minus tm. Ts minus tm is going to be minus c2 by 2. Okay. So basically we found ts minus tm. Now we need to find q yes, qs double prime, which is nothing but surface heat flux or wall heat flux. For that, we will use the definition of wall heat flux. We already did that in terms of convection. Now we can write it in terms of convection. Okay, wall heat flux is nothing but k times dou T by dou R at R is equal to R naught. Okay, this is your wall heat flux from Fourier's law of conduction. Now we already know T. T is again Ts plus C2 into, maybe I will write it down here so that it's easy. So T is Ts plus C2 into 1 minus R by R naught square. Okay, so this you can write it as Ts plus C2 minus C2 by R naught square into R square, so that you can easily do the math. So if you differentiate this temperature profile with respect to R, it is going to be simply minus 2C2 by R naught square into 2R, right? So you can write this as minus 2C2 uh, by R naught square into R. We have to substitute it at R equal to R naught. So if you do that, 2 into C2 by R naught. Okay. So R becomes R naught, and you can cancel the R naught by R naught square. So it becomes 2C2 by R naught. So we found both of them. We can directly find H. H is nothing but Q double prime S divided by Ts minus Tm, which is nothing but Q double prime S is minus 2 C2 by R naught divided by Ts minus Tm is minus C2 by 2. At the end of the day, we need to get Nusselt number to be constant, because this is a fully developed flow, right? If it comes to be constant, then we are right with our math. So this and this goes away. Negative to sign, you can remove it. Then this becomes 4 by R naught. Okay, this is your H. Let's substitute in Nusselt number. NUT is equal to, what did we found before? It's H into 2 R naught by K. Okay, let's write that H into 2 R naught by K is equal to, H is 4 by R naught, and I think somewhere K is missing. Yeah. So here we have K, right? So here, K should be here too. Here also K. So if that is the case, then you have, where is this? Minus 2kc2 by R naught. So here also you will have K, and here also you will have 4k by R naught. So if this is the case, this will be 4k by R naught into 2 R naught by K. So R naught cancel, K cancel. This becomes 8. So this is how you find the Nusselt number given velocity and temperature profile. Okay. We don't need to know whether it's a constant wall heat flux or it is a constant wall temperature. Given Ts and given temperature profile and velocity profile, you can derive your Nusselt number and you can use it forward. Okay. Any questions on this derivation? We didn't perform much. We just did the balance at the surface. Basically, this in terms of you know uh, physical law that we used is this one, Newton's law of cooling, and also the Fourier law of heat conduction. Basically, we did the energy balance. The wall heat flux, whatever the heat flux coming or going out uh, at the wall is going to be the same as the temperature Fourier's law of heat conduction. Uh, that's the one law that we use. So basically, this is nothing but K into dou T by dou R at R equal to R naught is equal to H into Ts minus Tm. That is one thing we did. And the other thing is we use the definition of Tm. That's it. Uh, because we defined heat transfer coefficient or the wall heat flux in terms of Tm. So we need to use its definition in order to derive this Nusselt. Okay. So if there are any questions, please stop me anytime. Mhm. And if there are no questions, maybe I will move forward with the second one. So in the second one, it is same as the parallel plate, a flow between a parallel plate. But only thing is for constant heat flux. But only thing is we did it for Hagen-Poiseuille's flow. Sorry, here it's a Poiseuille's flow. Now we are going to do it for a plug flow, where U by U bar is just one. Okay, so basically show that to you. We are going to repeat this calculation for the plug flow. U by U bar is 1. Okay. All right. Let's do it. That's what the consider flow of liquid between parallel plate with constant wall heat flux. The flow could be approximated to plug flow and the fully developed both thermally and hydrodynamically. Using energy equation, derive an expression for temperature profile and evaluate the Nusselt number. So we are going to do both. Um, so initially, we will start with energy equation. So which is going to be U into dou T by dou X plus V dou T by dou Y into alpha times dou square T by dou X square plus dou square T by dou Y square. So here we know for constant wall heat flux, this is going to be simply dTm by dx, right? And we know that this is going to be 0 for a fully developed flow. And we know this is going to be again 0 because the temperature gradient along x is 0. Sorry, temperature gradient along x is constant. So this is what we did for constant wall heat flux. You can see. So for constant wall heat flux, dTm by dx is constant. So if that is the case, dTm by dx is constant, then dou T by dou x is constant. If dou T by dou x is constant, then dou square T by dou x square is 0. Okay. And yeah, all right. So now if you simplify this, it becomes u dTm by dx equal to alpha times dou square T by dou y square. And we would like to express this in terms of non-dimensional temperature and also the y coordinate. So then this becomes theta is, we define it as T minus T wall divided by T mean minus T wall, right? And hence you can write dou square T by dou y square to be T mean minus T wall times d square theta by dy square. Okay, so we already know theta is not a function of x, right? That's what that we already saw it before. Where did we prove that? So that's why I was able to write d instead of partial derivative. So if it's a fully developed flow, we already proved that theta is not a function of x. Okay, now uh, so right hand side is taken care. The left hand side dtm by dx. So dtm by dx is constant, and we can write this as constant wall heat flux divided by perimeter times m dot into Cp. I think this also we simplified it a bit. So yeah, here it is. So we took that the width is very much greater than the distance between the two plates. So when you perform this, it becomes wall heat flux times rho Cp u bar h, right? Where u bar is the average velocity, and wall heat flux is again T wall minus T bulk mean temperature divided by rho Cp u bar h. So let's substitute it in the equation. So it becomes u times, you can write u by u bar h T wall minus T mean divided by rho Cp capital H is equal to alpha is k by rho Cp, k by rho Cp into T mean minus T wall d square theta by dy square. Okay, so we know this and this, you can cancel them, and so you can take this to this side and you can cancel them, it becomes negative, so you take everything to the other side. What would happen then? Then this becomes d square theta by dy square. Okay, so d square theta by dy square, and plus u by u bar times h by capital H k equal to 0. This is your equation. Now we also know y is nothing but, or y bar is nothing but y by h. Again, non-dimensionalization. So if you do that, then becomes d square theta by dy bar square. So then this will be h square, 1 divided by h square, plus u by u bar h by hk equal to 0. So now you multiply both sides by h square. So this becomes d square theta by dy square, so multiply by h square. Then this becomes u by u bar h square by hk is equal to 0. So this part is nothing but your Nusselt number based on h, and your Nusselt number again remains constant. So it's very nice to express this equation in terms of Nusselt number so that you can know that this is a constant and you can easily integrate them. Nu h equal to 0. So this is your final equation. I think this is the same thing that we derived here. Yeah, there is no difference. So and here we applied u by u bar to be based on Poiseuille's flow. Here we are going to apply based on plug flow. So for plug flow, so you know for plug flow it's nothing but plug flow is nothing but your velocity profile is uniform, even if it is inside the in between the parallel plate. So your velocity profile is nothing but u bar, the mean velocity, and it's constant throughout. So for plug flow, u by u bar is going to be simply 1. Okay, and now again you can simplify it further: d square theta by d y bar square plus nu h equal to 0. Now you can simply integrate them: d square theta by dy bar square is equal to minus nu h, and d theta by dy bar is nothing but minus nu h y bar plus some constant c1. You integrate it further: theta is nothing but minus nu h y bar square by 2 plus c1 y bar plus c2. So this is your general solution. Now you apply boundary condition. So boundary conditions are, so this is a parallel plate, right? So probably I didn't draw any. So you have this parallel plate. So this is 2h. This is minus h2 plus h x y. Okay. So at here, this is t wall, right? So basically at y equal to h or y bar equal to 1, at y equal to h, which is nothing but y bar equal to 1, your t is t wall, and if that is the case, theta is nothing but 1. Okay, theta is t minus t wall by t mean minus t wall. Uh, in that case, sorry, so t minus t wall means t wall minus t wall, right? So this becomes 0. It's not 1. Okay, that is one. And also this is wall condition. The other is symmetry along the uh, x-axis. So that we know at y equal to 0, which is same as y bar equal to 0. We know that dou t by dou y is 0. So if that is the case, we know that d theta by dy bar is equal to 0. Okay. Um, which means it's reaching a maximum or minimum at the uh, center line. Okay. Now let's substitute these boundary conditions. If you substitute, so let's say if we substitute the let's substitute the second one first, or anything first. It doesn't matter. No, let's substitute the second one so that it is easier for us to solve. So if we substitute the second one, we already know d theta by dy bar. D theta by dy bar is nothing but minus nu h y bar plus c1. Now if you substitute at y bar equal to 0, this becomes 0 plus c1 is equal to 0. So this gives c1 equal to 0. Okay, now it simplifies it further. Now at y bar equal to 1, theta at y bar equal to 1 is nothing but minus nuh by 2 plus c1 is already 0 plus c2, and theta is nothing 0, so you can write c2 to be nuh by 2. Okay, now you substitute them in theta is minus nuh y bar square by 2 plus nuh by 2. So this becomes You can take NUH by 2 constant. So you can simply express theta to be in terms of NUH by 2 into 1 minus y bar square, where y bar is y by h. Okay. This is your temperature profile, but we also need to find the Nusselt number. Now, that was a problem we were facing during the class too. We use this and we end up having theta to be a function of Nusselt number and y bar. That is exactly we also have. We have this f2 function. In our case, the f2 function is nuh by 2 times 1 minus y bar square. Okay. Now, we need to find nuh, right? Without nuh, you cannot find the temperature profile. But we have used both the boundary conditions. That is not, um, you know, but those two are not, unique boundary conditions. So one is just a redundant constraint. Because of definition of theta, you will end up having y bar equal to theta equal to 0 at y bar equal to 1. So we need to have one more condition for this to be closed. That is what we did. We use the definition of Tm. Okay. Uh, Now, if you use this definition uh, and if you perform this calculation, we end up having another constraint called integral of 0 to 1 f theta dy bar equal to 1. Okay, so this constraint you need to satisfy to get NUH. So once you find theta, we know f is nothing but u by u bar. U by u bar is 1 for us. So integral of 0 to 1. Let me write that down. From the definition of Tm, uh, so I mean I can repeat this calculation, but for sake of simplicity, I will take the final thing that professor already derived. It's going to be f times theta dy bar equal to 1. Right? That is what the final. This is one of the conditions that you need to satisfy. This is from the definition of Tm. Now f is nothing but u by u bar, which is 1 for us, and theta we already found. So let's say if we substitute that, integral of 0 to 1 theta dy bar is equal to 1. Now integral of 0 to 1 theta is nuh by 2 into 1 minus y bar square dy bar is equal to 1. Okay. Now you can integrate it with y bar. NUH is constant, you can take them out. NUH by 2, integral of 0 to 1, 1 minus y bar square dy bar is equal to 1. And how do you integrate this? NUH by 2 into first is y bar, so it becomes simply y bar 0 to 1 minus integral of y bar square dy bar, which will be y bar cube by 3. Y bar cube by 3. You apply the limits here. This should be equal to 1. So this becomes NUH by 2 times 1 minus 1 by 3 equal to 1. This becomes NUH by 2 into 2 by 3. 2 get cancelled. So this finally gives you NUH to be equal to 3. Okay. So this is your Nusselt number correlation based on H. I think we also define hydraulic diameter. Hydraulic diameter is nothing but 4 times Nusselt number based on H. So this becomes simply NUDH is going to be, simply 4 times NUH, which is going to be 12. So if it's a plug flow, the Nusselt number is going to be 12. If it's not a plug flow, if it is a Poiseuille flow, then your Nusselt number is going to be 140 by 70. So it's a little bit, I guess, less than 10, probably like 8 to 9. And if it is plug flow, you are going to have 12. Okay, for the same constant wall heat flux condition. So based on your temperature profile, here we derive the temperature profile. Here again, F1, if we integrate it, we will end up having temperature profile. Here, I also didn't do, professor also didn't do, because this is a simple integration. Probably we did. Uh, you can do it and express this and see for yourself what is the temperature profile you're getting, and for that temperature profile and the given velocity profile, you will end up having different Nusselt number uh, Nusselt number uh, values. Okay, so this is how you perform this calculation. And actually, constant heat flux is fairly easy, and you can derive the analytical solution. However, if it's a constant wall temperature, then we may need to rely on computers and also numerical methods in order to solve this problem. Okay. Um, all right. I hope these two problems would give you confidence in terms of solving a similar convection problems. I also strongly urge you to solve the constant wall temperature using MATLAB, or even Python, whichever you are familiar with, and see for yourself what Nusselt number you are getting. Okay? It would be an interesting exercise for you to do such calculations, the shooting method calculation. Okay. All right. This is what I have today. I hope this is helpful. If you have any questions on these questions or of these two problems that we solved today, or if you have any questions related to the derivations or uh, course content, feel free to stay back and ask. If you have no more questions, then we will meet next week. Probably it will be natural convection and also viscous dissipation. Okay. All right. Thanks, Avinash, Shivam, and Krishna Kumar for attending. If you have any questions, please stay back and ask. If not, we'll meet next week. Okay. Bye bye.
Sir, I have a doubt in last week assignment question, sir.
Give me a second. Mm, For
Sir,
some reason, it's one second.
sir, I think the option is there is a error, sir.
Which question?
Question number 5, sir.
This week's question is it?
No, sir, week 8, sir.
Week 8. Okay. Give me a minute. Let me open it.
Yeah, sir. No, no problem, sir.
Oh, this one. Okay.
Yes, sir. Actually, the option was a wrong error, sir. Option D also it is mentioned it is accepted at the sir.
Oh, okay, okay.
That's it. Assignment answer it is partially correct, sir. That's why I
Oh,
just
okay,
want to
okay.
inform you, sir.
Okay.
Okay,
Oh,
sir.
it
Nothing
can't
else, sir.
be, right? If A and C is the right answer, then D can't be the right answer.
D can't
Yeah.
be, sir.
Yeah,
That's
yeah.
it, sir.
It might be a small problem from the NPTEL side. They will correct it. Have you raised
Okay, okay,
this
sir. Okay, sir.
problem in the common forum?
No, sir. Not yet, sir.
Okay, maybe what you can do is you can formally request this problem in the forum. uh, they
Okay,
will,
sir.
yeah, they will look at it. They might be probably looking at it already, but I
Okay,
would
sir.
request you to
Okay, sir.
write an email in the common forum telling that there is some inconsistency with the accepted answers, and
Okay, sir.
ask them to uh, please look into it. Okay.
Okay, sir. Okay, sir. I'll do it,
Yeah.
sir.
So A and C, yeah,
Okay.
expressed in terms of enthalpy, then enthalpy in terms of temperature. We'll derive energy equation in terms of entropy and then entropy in terms of temperature. Okay. So I think B is the right answer.
B is true, sir. A and B are
Oh,
wrong,
okay.
sir.
Okay, okay, okay. A
Question
and C are
question asked
wrong.
is which of the following is wrong?
Wrong, wrong. Okay, okay. So then A and C is
Then A
the
and
should be the
alone, sir. B will not be there, sir. That's it.
yeah.
Okay, sir. I'll
Okay.
rise in
Yeah,
the
yeah, yeah.
forum, sir.
Yeah, sure. Thanks for
Okay, sir.
bringing this up. Yeah. Please write it in the
Okay,
forum.
sir. Thanks. Okay, sir. Sir, in exams, what will be the pattern
So it will be same
they
as
will
your
ask?
assignments. So whatever kind of
Okay, sir.
questions that
Similar.
you see in the assignments is what you will
Okay,
also
sir.
see in the exams. Okay.
Okay, sir.
Sometimes you
Similar
will be
pattern.
asked to. Sometimes there will be a
Uh,
small derivation also, like we did today. Um, there might
okay,
be
sir.
some small derivations. Um,
Okay, sir. Okay, sir.
if not, it will be similar to like this. Okay.
Okay, sir. Sir, everything will be into 1 mark or 2 mark like that only, sir?
Yeah, yeah, yeah. Same as your
Oh, oh.
assignments. It will be 1.2 point thing. Yeah.
Okay, sir. Okay, sir. Okay, sir.
Okay.
Okay, sir. Thank you, sir. Thank you, sir.
All right. Bye, bye, Avinash. Thanks for joining.
Thank you, sir.